Afternoon, nerds, and welcome to the very first AP Pre-Calc lesson. Aren't you excited? I'm amped. The very first lesson, lesson 1A, and if you keep going, turn a couple pages, you'll see we do have a 1B, so we're not going to finish this whole lesson in one day, is called Change in Tandem. And in tandem just literally means together. So the very first lesson is all about how things change with relationship to each other when we talk about functions and stuff like that. So how x is changing with y, or how y is changing with x, and how curvatures of graphs are changing, slopes of graphs are changing, just things like that. Change in tandem. It's a really big deal to AP. So very beginning, talking about something that you should already know and love, and that's what a function is, right? A function is a mathematical relation that maps a set of input values, usually x's, to a set of output values, usually y's, such that each input value is mapped to exactly one output value. So the definition of a function, for every x, there's exactly one y. And you're supposed to already know that from Algebra 1 and Algebra 2. For every x, there's exactly one y. It says each input maps to exactly one output. So every x gives back exactly one y. All of your inputs, this is review, is called the domain. So your x values that your graph can use, or the x values that your graph can cover up, is a domain. The output values is called the range. This is all the y values that the graph uses or covers up, however you want to talk about it. I'm going to be real with you. I've never heard of this rule of 4 until last period when I looked at this. Because I didn't write these notes. You know, Ms. Stinson and I, we purchased said program. So sometimes I'll disagree with it. Sometimes I'll write, you know, like, hey, let's scribble that out and change that, just so you know. But this rule of 4, no one's ever going to say what's the rule of 4, but it's just talking about the 4 different ways that you could represent a function. You could do it with a graph. You could just do it with numbers, and that's usually like you see a table of data. Let's see if I can get one in here real fast. Well, a table of data just has a bunch of x's and then a bunch of y's, okay? Algebraically, well, that would be typically your function equation, right? Your y equals mx plus b's, or your ax squareds plus bx plus c's. That's going to be your algebraic representation. And then words, I guess you could, if you wanted to, verbally describe, and you could say that, you know, x varies directly as the square of, you know, so that would be verbally. We're going to focus on the first 3, not so much the last one, so don't stress out about the words. Starting out pretty darn easy. We got f of x is 2x squared plus 5x, and our job is just to evaluate. Hardest part about this is, do you understand how to read function notation and what you're being asked to do? This is f of x, so this is asking me to just take this and add it to f of 3. If I say f of 3, what are you being asked to do? You can shout it out. Just plug in 3. So we're going to take our original function, and we're going to add it to whatever we get when we plug in 3. Just so you know, this f of 3, this is actually saying, what is y when x is 3? You know, this is just Algebra 1, Algebra 2 stuff here. So let's go ahead and find f of 3. You know what? Actually, let's do it all at once. Let's do it all at once. That'll be fun. Our original f of x, 2x squared plus 5x. And then we're going to add f of 3. So this is saying everywhere you had an x, plug in a 3. And I'll do that in another color. So we've got 2. There's going to be a 3 there. Plus 5. There's going to be a 3 there. Of course, these aren't going to be like terms. These won't have any x's. So we have 2x squared plus 5x. And following the order of operations, square first. So 9 times 2, 18. So anyway, I'm sorry, I did pause the video. So is it recording again? It is, good. So 3 squared, 9 times 2, 18. 18 plus 15 is 33. There you go. So nothing crazy going on. Notice here when I use this 3 for substitution, I used parentheses. Please be in the habit of using parentheses every time you substitute. If you don't use parentheses, sometimes you'll get in trouble work-wise. Like, say this was a -3. If you hadn't used parentheses, you might have forgot that you had to square the negative before you multiplied and things like that. if you don't use parentheses when the IB, excuse me, this is AP, when the AP graders are grading your free response stuff, they might actually mark you off for sloppy symbolism. So don't do that. Every time you're going to substitute, please use parentheses. So just like when we said f of 3, this is telling us plug in, substitute in 2x. So everywhere you hit an x, open a set of parentheses and drop in that 2x. So 2, set of parentheses, plus 5, set of parentheses. Replacing x with 2x, which is actually a transformation, if you can remember back to your Algebra 2 days. Squaring the 2 and the x gets us 4x squared. And then 5 times 2x is just 10x. So lastly, just multiply these two. 8x squared plus 10x. Out of curiosity, does anybody remember what transformation that is? Replacing x with 2x? It's a horizontal change because it happened on the inside to the x's. And it's a multiplication. So that's a dilation. It's actually a horizontal shrink. Factor 1/2. But we'll talk about all that when we review transformations. Do it again. Hey, look, remember what I was talking about with the negatives? Boom, there it is. So, everywhere we had an x, drop a set of parentheses, fill it with negative x. Simplify. See if you can get there before I do. Order of operations says square first. So this negative x, quantity squared, just becomes negative x times negative x, which is x squared. So I'm going to get 2 times x squared, and 5 times negative x is just negative 5x. That's also a transformation. Reflect over y-axis, because the x has changed from positive to negative. And the last one, also a transformation. This is shift left 3. Might as well review while we learn, right? Everywhere you had an x, open a set of parentheses and throw in that x plus 3. And this one, yuck, is going to make you FOIL because of the exponent. What color have I not used yet? Orange. This one's my orange and blue one. Go Gators. Here, this is not x squared plus 9. Please don't do that. Please don't say that. This is not x squared plus 9. This is x plus 3 times x plus 3. You are going to have to distribute, FOIL, whatever you want to call it, and combine like terms. Since this is AP, I will not make a habit of doing this, but I am going to remind you what this would look like. Usually I would just write what this is. But x times x, x times 3, 3 times x, 3 times 3. So it's going to be x squared plus 6x plus 9. And then here I could just distribute the 5. All that's left to do is distribute the 2 and combine like terms. 2x squared, 12x. All right, I'll be able to combine 12x and 5x and 18. I'll be able to combine the 18 and the 15 at the end. 12 and 5, 17, and 18, 15, 33. There it is. What do you think about substituting and evaluating, simplifying, things like that? It's not scary hard, correct? And we're not reviewing transformations anyway, so if you didn't remember them, it's not a big deal. It's just cool if you are thinking that. We're only going to do part A today. So I chose homework questions from the practice set that you picked up. You'll have to go onto Schoology, onto the calendar, and click on the little ribbon for the assignment to see what questions I wanted you to do in set 1. And then tomorrow, we'll do set 2, and you would click on the little ribbon on the Schoology calendar to see what questions I want you to do in set 2, and you would turn in the practice set afterwards. And of course, if you have any homework questions while you're working on it, shoot me a message over Thrillshare Rooms. But I've put the answer key online already. So check your work with the answer key. And if you don't understand why something is what it is, please reach out. If you think there's a mistake in the answer key, please reach out. Okay? I want to change those things if they're not right. I guess this could be considered the table of data, the numerically, instead of seeing it as a row of x's and a row of y's. So what we're going to do on this page is we're going to find the domain of each of these functions that we're looking at. If a function f is defined by an equation and no domain is specified, then the domain will be the largest set of real numbers for which the value of f of x is a real number. Essentially, we're just saying if you could plug in an x and get a y, that's part of the domain. Exclude any real numbers from a function's domain that cause division by 0. Never try to divide by 0. That's big fat no-no. Or that result in the even root, so like square root, 4th root, 6th root, of a negative number because imaginary, right? So don't try to divide by 0, and don't try to take the square root of a negative number. Can't do those kinds of things. It says determine if we're looking at a function. Finding the domain of a function and then determine if it's a function, I don't feel like that's kind of not good. So no guarantees that these things are functions. We're going to figure out their domains, and then we'll talk about yes or no a function and why. So a domain is just the list of all of the x's that exist for a relation. These are the only x values that exist in this domain. Because these are not coordinates and because it's not a span of numbers, I can't use interval notation for a list of numbers. I have to use set notation, and that's what you're looking at here. These are called braces. These fancy parentheses, these braces, that's for set notation. So your domain consists of the set of, and if you don't know how to draw one of those, it's like a tall, narrow S without picking up your pen, tall, backwards, narrow S. That's how you make your braces. Consists of the numbers that I underlined in red. They need to go in numeric order from small to big, just like you were trying to do an interval, small to big. So what's my smallest one? -3, then 1, 2, 3, 7. There you go. Did any of the x's repeat? You guys can just shout it out. No. Because no x is repeated, we're guaranteed that this is a function. So if I had a repeated x, would it then not be a function? Not necessarily. The definition of a function is for every x, there's exactly one y. So if I repeat, let's just say x equals 7. I repeat x equals 7. If I say the point 7 comma -2 again, it's still a function. Because for the x value of 7, there was only one output, and that would have been -2. However, if you repeat an x and you have a different y value, you've broken the rule of for every x, there's exactly one y. So let's just say, for sake of example, 7 comma 0 was in the list. Now it's not a function because the x value 7 can only give you one y value. Think about the inputs as being commands on a calculator. It doesn't matter how many times I do 1 plus 2 on this calculator. It is always going to give me 3 as my output. You see, the input 1 plus 2 has exactly one output. That means this thing is functioning, if you'll pardon the joke. Not even a giggle? It's It's all right. I'll have to go home and tell my wife. She'll laugh. For every input, there's exactly one output. Could you imagine if like 1 out of 1,000 times I typed 1 plus 2 and it said 5? If every now and then the input 1 plus 2 told you a different output, I think we can all agree that you can no longer trust this calculator and you can say there's something wrong with it, right? Because it would not be functioning properly. I think that's hilarious. But anyway, for every input, there's exactly one output. But here's the thing. We all know that there's other ways to get this output. That's not a problem. You can have all kinds of different x's, all give you the same y. Nobody cares. That's not an issue. The issue is if this deviated, and this didn't. Okay? So inputs can only repeat if they give you back the exact same output that they did last time. So if you don't see a repeated input, it's automatically a function. Cool beans? Okay. Here, just be looking for a class of like 23, 24 voices shouting out yes or no. Class, is this a function? No. I said 23, 24 voices and I got like 7 voices. That tells me I have a bunch of people that don't know. They don't know, and that's okay because we're practicing. This x points at exactly 1 y. No issues. This x points at exactly 1 y. No issues. This x points at, 2 different y's. What is bad boys 2 timing? This is not a function. This right here is a problem because it points at 2 different outputs. Every now and then this calculator says 1 plus 2 is 5. Okay? So this is not a function. You want to determine its domain? It's these numbers right here. They're already listed for you, and they're in numeric order. -6, -3, 2, and 3. I guess I should have done that first, but I got so excited talking about functions. -6, -3, 2, and 3. So that's its domain, but this is not a function because the input of x equals 2 points at 2 different y values. Not allowed. By the way, if you'd plotted every one of these x comma y's, 2 comma 0 and 2 comma -2 would have been perfectly vertical with one another. So this thing would fail the vertical line test. If you can remember that all the way back to Algebra 1 days. Questions, comments, concerns on lists of numbers or this like map setup? Not bad, right? I actually did this with Algebra 2 Honors today. Is this a function? Hey class, is this a function? So many people not answering me. It's because they don't know. How do we identify a function if you're looking at a graph? Well, the rule is for every x, there's exactly 1 y. So x equals a number could be graphed as a vertical line. If any vertical line that exists on the graph touches the graph exactly once, it is a function. So because this passes the vertical line test, it is a function. Because B/C is because. VLT will be the vertical line test. Every vertical line that I draw that goes through that graph goes through it only one time. But what is its domain? Domain would be the x values that the graph covers up. Imagine there was a bulb, a lamp up here casting shadows straight down onto the x-axis, and a lamp down here casting shadows straight up to the x-axis. Whatever parts of the x-axis would have a shadow on them, those values are your domain. This is a closed dot. So what that tells me is my domain begins at that number, includes that number, and this arrow says the graph goes forever to the right. My domain is everything to the right of and including -4. For inclusive, remember, we use brackets. And since the graph never stops as it goes to the right, it is heading towards positive infinity. Please recall that you never put a bracket on infinity because infinity is not a number. It is a goal that the graph will never reach, but it'll forever try. What do you think? Light work, he says. That's what I like to hear. Light work. This graph has a hole in it. That's what that little thing there is showing you. It does not exist at the coordinate 2, 5. This is a vertical asymptote. This is a horizontal asymptote. Hopefully you remember some of those things from Algebra 2, but we'll cover them later on in the year, but that's what we're looking at. Let's do the easy one first, and that is whether or not it's a function. And I'm looking for lots of voices, everybody in the room. It's a simple yes or no, and I don't know who's right and wrong because I'm not, able to pick out a single voice in a crowd. But class, is this a function? Yes, it is. This is a function because of the same reason this is a function. It will pass the vertical line test. Every single vertical line that I could draw that actually goes through the graph would go through it once and only once. So function. Now it's domain. This graph has a hole in it at the number x equals 2. It exists forever to the left of x equals positive 2. So here's how we would say that. From negative infinity up to the number positive 2. It doesn't exist at 2 though, so I can't put a bracket there. It exists after 2 though. Between the numbers 2 and 4 it exists. It'll never get to 4. It'll approach it forever, but it'll never get there. So we're going to string these intervals together with union symbols. It's just a fancy U hopping over the number 2 with the union, and we're going to head towards 4. We'll never get to x equals 4, but we will freaking try for all eternity. And then, if you pop right over the number x equals 4, the graph exists again, everywhere to the right of x equals 4. It's down here now, but who cares? It exists. So hop over the number 4 with the union as well, and head towards positive infinity. And then we'll pause there, not actually pause, but hit the button. But I'm going to ask, is there anything that I can help you with? Any questions I can answer? Anything I could say better, say again in a different way? Anything like that? Okay. All right. This is a quadratic. It factors. I see a GCF of x. Since the front number is positive, it's a 1. Since it's positive, I know that this U-shaped graph points up. 0 makes this 0. Negative 3 makes this 0. This graph crosses the x-axis at 0 and at negative 3. This is a quadratic, so it has an axis of symmetry. That axis of symmetry would be halfway between its two zeros. Halfway between 0 and negative 3 is negative 1.5, right? So you would need to plug in negative 1.5 to see where that lands, and I'm not trying to do that in my head. I mean, I could, but why? Oh, you can't see what I'm typing. Negative 2.25. Is that a function? Yes. Lots of voices. Come on, guys. Yes. Yes, it is. Function. And what's its domain? All real numbers. All quadratics have the same domain. All real numbers. Negative infinity to positive infinity. Boom. There it is. This is a square root graph. Square root graphs have a starting point, and then they kind of look like a shooting star. They could go up or they could go down. They could go left or they could go right. This one goes up and to the right. This is a square root graph. I can tell you that I know it goes up because the number that sits in front of the radical is positive, so it points up to the positive y's. And I can tell you it points left because the number that's in front of the x is negative, which is on the left side. So this graph points up and to the left, so it's going to look something like this. I'm going to graph in purple. It's going to look something like this. Up and to the left. Like I said, I know it's up because the front is positive. I know it's left because the number in front of x is negative. That comes with the knowledge of transformations. For now, let me ask you, is that going to be a function? Of course it is. Just like this square root graph, it's a function. All square root graphs are functions. I'm not even going to bother sketching it. I'm just going to know it looks like that, which means I know it's a function. The hardest part about this is finding its domain algebraically. And it says square root of some stuff. And what kind of stuff are you never allowed to take the square root of, even with a calculator? Negative numbers. So we know that 4 minus 2x can't be negative. If 4 minus 2x can't be negative, what could it be? It could be positive or it could be 0. So how do we say that 4 minus 2x is positive or 0? We just say that 4 minus 2x is greater than or equal to 0. You can take the square root of 0. You'll get 0. Now let's get x alone. Subtract the 4 from both sides and divide by negative 2. Please remember that when you divide by a negative number or multiply by a negative number, across an inequality, it flips the symbol over. X is less than or equal to 4. See? To the left. So this number right here, this would be at 4 commas. Can I not do basic math? Sorry. Can't do basic math. That'll be at 2 comma 0. See, if you substitute x equals 2, you get 4 minus 4. Square root of 0 is 0. That means I know the range too, but the question didn't ask. We're not going to leave our domain in inequality format. We're going to move it to interval notation. This graph will go forever to the left. Just like going forever to the right gets you to positive infinity, forever to the left gets you to negative infinity. Our intervals are always going to go from smallest to biggest. And there is nothing smaller than negative infinity. And it's going to come all the way up to x equals 2 and stop there. Not bad, right? I mean, honestly, all we're doing right now is Algebra 2 stuff. I basically taught this lesson in Algebra 2 today. Increasing, decreasing, and constant. You should have covered increasing and decreasing in Algebra 2 honors, or maybe MCA. I don't know if you covered constant, though. Increasing essentially means your graph is going up as you go from left to right. Decreasing essentially means you're going down from left to right. And constant means, well, flat from left to right. Now here are fancy definitions. F of x is increasing on an interval I for any 2 points in the interval. A positive change in x results in a positive change in y. It basically says as x goes up, y goes up. That's what that means. As x goes up, y goes up. So as long as a is less than b and f of a is less than f of b. So as long as the x's went up and the y's went up, increasing. In my Algebra 2 class, I teach it as a roller coaster from left to right. If your roller coaster had to go up as it went from left to right, that was increasing. A calculus definition of increasing is anywhere where your slope is positive. But that's the same thing as saying the graph is going up somehow. Decreasing. Everything is from left to right. So as x gets bigger, as x gets bigger, y gets smaller. So that's going down as you go from left to right. If it's a roller coaster, as you go from left to right, your roller coaster's falling. Whee! Okay? In case it's a curve and not a straight line. The fancy definition says, for any 2 points in an open interval, a positive change in x results in a negative change in y. As x goes up, y goes down. And constant says, as x goes up, y doesn't change. So it's horizontal lines, essentially. That's constant. Cool? Now, I've talked about this roller coaster a couple times. Imagine this was a roller coaster, right? And here's you chilling like you do. And, you know, you're having a blast. And you're going that way. And like I said, you're having a blast. As soon as I let this roller coaster go, is it going up or down? Lots of people. Come on, everybody. Up or down? Down. It is going to stop going down at an x value, correct? At what x value does it stop going down? Just shout it out. 0. Because at 0, I've reached the bottom of this hill, so to speak. And I got to start going back up, right? Here we have an issue. Right there. At this point, if I took a snapshot and there wasn't any like wind, you know, obvious through someone's hair, is it going up? Is it going down? Or is it doing both? That's the question. And AP wants you to say it's doing both. It's going up and down at this instant. Okay? That's what this says. Basically, when you're talking about your increasing, decreasing, you put a bracket when it changes between the two. And your endpoints, as long as they exist, like this is not an endpoint because it's an arrow, but let's just say it was a closed up dot, that would also get a bracket. Okay? If you guys are cool with it, I'm not going to color it. I'll just, you know, like write in color. I don't feel like coloring the ref. So let's talk about where it's increasing. Well, you've already told me that it's decreasing here. Decreasing is red. So it starts out here at the negative infinity and goes up to 0. And we have to bracket where it changed. Is that the only time that it's decreasing? No. Since I have the red pen in my hand, I'm going to go ahead and finish this one. The next place where it begins decreasing is here at x equals 5. And this arrow that heads to the right tells me as I go to the right, my graph never stops going down. Now you guys told me that I'm increasing here, starting there. Just shout it out. At what x value do I stop increasing? 2. Good. And what's happening then from 2 to 5? Constant. I want you to do that in yellow. We'll see how that looks. Is that legible? Can you read that? That's not bad. It's brighter on my end. From 2 to 5, you're constant. And then this thought is just, this is like, oh, what do you think about the intervals stated? But it just, again, when we have a change in increasing, decreasing at a coordinate, as long as the graph exists at that coordinate, you're going to use a bracket. If this had been an open dot, the graph doesn't exist there, then it would have been parentheses on this 2. Or no, on this 0, excuse me. Okay? So in general terms, we could say that a function increases over an open interval of its domain if its graph rises from left to right, decreases if the graph falls from left to right, and constant if it's horizontal. It is important to note that the intervals refer to only the x values when the y values are increasing, are decreasing, or are constant. We use our x values to say where are things occurring. Okay? All right. Thank you so much, nerds. I think that's a successful lesson.